Welcome to Visual Algebra Lecture 8.3, Units and Zero Divisors. A unit is an element in a ring that has a multiplicative inverse. Rings that have only units, except for zero, of course, are called division rings. Commutative division rings, like the reals, rationals, and complex numbers, are fields, and non-zero ones, like the Hamiltonians, are skew fields. A zero divisor is an element that can be multiplied by a non-zero element to get zero. When a ring has non-zero zero divisors, basic properties that we take for granted, like cancellation, can fail. Rings that have no such elements are called integral domains. After introducing these concepts, we'll see some more examples of rings, such as group rings and quadratic integer rings. We'll finish by proving that every finite integral domain is a field, which is one reason why finite rings aren't given much attention in most books and classes. Okay, let's get started. Informally, a ring is a set where we can add, subtract, and multiply, but not necessarily divide. A unit is any element u in a ring that has a multiplicative inverse, that is, some v for which uv and vu are equal to 1. Sometimes we write v inverse equals u. So think of the units as the elements that we can divide by. And we'll often write the set of units of a ring as u of r. And that is a multiplicative group. Here's a very basic but important fact. If an ideal of a ring contains a unit, then that ideal must be the entire ring. Let's prove that. So let's take a unit. U, which is in the ideal I. And what we'll show is that for any element in the ring, that element has to be in I as well. So for any element little r in big R, R is, well, now what can we say? I is closed under multiplication. So here's what we're going to do. We're going to take, so everything on the form blank times u is an I. So what can we put in here to get r? Well, if we put a u inverse here and then an r, so in other words, r u inverse, notice how that product is equal to r. And so that's an I. And therefore I is all of r because we took an arbitrary element in the ring. Let's do some examples. So to start, let's take the ring of integers. What are the units in here? These are the elements that we can divide by. You probably see it. -1 and +1. Okay, example 2. What about r equals, let's say, z10? So what sort of things can I, in z10, have multiplicative inverses? Well, I'll show you one and see if you can generalize this. So 7, I claim, is a unit because 7 times 3, mod 10, 7 times 3 is 21, which is equal to 1 in R. So we say that the multiplicative inverse of 7 is equal to 3. Do you see the pattern for what elements have multiplicative inverses? Notice how 2 will not, because every multiple of 2 is going to be even. We can never get 1. So let R be equal to Zn. Then K is a unit if and only if the GCD of n and k is equal to 1, things that are relatively prime to k. Remember earlier that we defined the group of units. I would call it UR, or so sorry, UUN. This is the group of things relatively prime to n. under multiplication, and that U was for the word unit. So what about the units of the 2 by 2 matrices over the real numbers? These are the set of invertible 2 by 2 matrices over the real numbers. After units, our next type of element to introduce are zero divisors. An element, x in a ring R, is a left zero divisor if x times some non-zero y is equal to 0. And we can define right zero divisors analogously. To be honest with you, I can never remember if this definition is left zero divisor or right zero divisor. In other words, do we say left because the element is on the left, or do we say right because we are multiplying on the right? At the end of the day, it doesn't matter as long as we're consistent, but this is the correct definition. I also want to mention that some books and sources require zero divisors to be non-zero elements. I think it's fine to say that 0 is a zero divisor. I think it's more consistent with the definition, but a few times I have to say things like, suppose that x is a non-zero zero divisor to properly state a theorem, but that's okay. That's just extra clarification. Let's do some examples. First, there are no non-zero zero divisors in the integers. With the other convention, some people will say that there are no zero divisors in the integers, but I don't mind this extra word for extra clarification. The zero divisors of Z10 are the numbers that are not relatively prime to 10, so 0, 2, 4, 5, 6, and 8. More generally, a non-zero element k of Zn is a zero divisor if and only if the GCD of n and k is bigger than 1. In Zn, all of the elements are either zero divisors or units, but that need not hold in general. For example, in the integers, we have 2 units, 1 and -1, 1 zero divisor, 0, and everything else is neither a unit nor a zero divisor. The ring of matrices over, say, the real numbers has zero divisors. For example, here are 2 by 2 matrices whose product is the zero matrix. There's many more. One particular type of zero divisor will be important later in this chapter when we get to prime, primary, and radical ideals. So let me just give the definition right now. An element in a ring is said to be nilpotent if some power of it is equal to 0. I want to take a few minutes to tell you about a rich family of examples of rings that can be constructed from multiplicative groups. Let G be a finite multiplicative group and R a commutative ring. Something usually pretty basic like the integers, reals, or complex numbers. The group ring RG is the set of formal linear combinations of group elements in G with coefficients from R. Multiplication is defined in the so-called obvious way. And by that, let me just give you an example. Let's consider the ring of integers and the group D4 and the following 2 elements in the group ring. So R plus R squared minus 3F and Y is -5R squared plus RF. The sum of these x plus y you get by just adding them term by term and like terms combined. So 1 R squared plus -5R squared is -4R squared. The product x times y, you just multiply them out as you would polynomials and combine like terms. So I'm not going to do this, but if you carry this out, you will get -5 minus 8R cubed plus 16R squared F plus R cubed F. So you apply the same relations as you do in the group, but you have coefficients from R. Here's a tip for how to think about elements in a group ring. I don't actually recommend writing them like this, but sometimes it's useful to think of things like this. So for every element in the group, we have a basis vector, and the elements in the group ring are just linear combinations of the basis vector. So instead of writing something like r plus r squared minus 3f, we can write er plus er squared minus 3ef. Here's another example of a group ring, because this one illustrates a really important subtlety. Consider the group of quaternions, G, and the ring of just real numbers. And now the group ring, RQ8, consists of formal sums like A plus BI plus CJ plus DK, and then plus E negative 1 plus F negative I plus G negative J and H negative K. And I want to emphasize that every choice of coefficients gives a different element in the group ring. For example, if all of these coefficients are 0 except for A equals 1 and E equals negative 1, well, then we get 1 plus 1 times negative 1, which is not equal to 0. This is why it's useful to think about things like this with that basis vector analogy. So you can think about 1 plus negative 1 in the group ring as E1 plus E negative 1, and that is different from just the 0 vector. In contrast, in the Hamiltonians, if you look at all elements of the form A plus BI plus CJ plus DK, and you write 1 plus negative 1, then of course that is going to be the 0 element. Therefore, the Hamiltonians and the group ring RQ8 are different. They're non-isomorphic. I guess this isn't a proof, it's just intuition for why they should be different. But here's a way that would establish it formally. It's a more general statement, though. So if little g is an element of finite order in the group, let's say it has order k, bigger than 1, then I claim that the group ring RG always has 0 divisors. For example, the product 1 minus g times 1 plus g squared plus ... g to the k minus 1, you multiply this out, it telescopes, so you get 1 minus g to the k. And if g has order k, that's just equal to 1 minus 1, which is 0. So this group ring, RQ8, has 0 divisors. The Hamiltonians, we know, does not, or non-zero 0 divisors. Notice that the group ring RG always contains a subring isomorphic to R. Now that's what you get when you, let's just do an example up here. If you set all of these terms equal to 0, and you just look at the coefficient of the multiplicative identity, and I should say, I don't think I said that R has unity. That's typically our default assumption unless we say otherwise. And that's one reason why the term that I defined in a previous lecture, RNG, rung, is useful. So if your null hypothesis is that a ring has the identity, then you can use the word rung if you want to emphasize that it need not have identity. Finally, the group of units of a group ring contains a subgroup isomorphic to G. And to see why that is, let's just do an example. And this is where it's helpful to think about the elements in here as being generated by the basis vectors. So E1, EI, EJ, EK, E negative 1, E negative I, E negative J, E negative K. These are elements in the group ring. Each one of them you get by taking this linear combination and setting 7 of the coefficients to be 0 and the other one to be 1. And this is going to be isomorphic to the group G. And everything in here is a unit, because if you have E little g times E little g inverse, you get E to the 1. Now that we've talked about several types of elements in rings, such as units and 0 divisors, let's talk about several types of rings. So if every non-zero element of a ring R has a multiplicative inverse, in other words, if the set of units is the set of non-zero elements, then R is a division ring. If R is commutative, it's called a field, and if R is not commutative, it's called a skew field. A division ring is a more general term that encompasses both of these. It just means that we can divide by anything except for 0. Examples of fields that we've seen include the rationals, the reals, the complex numbers, and ZP as long as P is prime. The Hamiltonians are, I think, the only example of a skew field that we have seen. Here is another example of a field that is not on this above list. I think I might have really briefly mentioned this back in Chapter 2. We'll see this more in Chapter 9 when we get to divisibility and factorization and do some basic algebraic number theory. A quadratic field is any field of the following form. We say Q adjoined root M, and this is the set of complex numbers of the form R plus S root M, where R and S are rational. And we can assume that M is not 0 and not 1, because otherwise, if it's 0, we just get the rationals, and if it's 1, we also get the rationals. And we can assume that M is a square-free integer, because if it's not, we can always just factor out a square. For example, root 8 we could just write as 2 root 2. This is clearly closed under addition, subtraction, and multiplication, but it's also a field because we can divide by anything that's non-zero. To see why, consider the element R plus S root M. And if we multiply by its so-called conjugate, R minus S root M, we get an integer, R squared minus S squared M. From here, we can see that the multiplicative inverse of R plus S root M is just this conjugate. Well, it's almost the conjugate. If you multiply those together, you get this integer, so you have to divide by this integer. So it's R plus S root M divided by R squared minus S squared M. And you can check that this denominator is non-zero given the assumptions up here. Here is another type of ring, and this is one of the most important ones that we'll see throughout this chapter and the next. It's called an integral domain. This is a commutative ring with 1 and with no non-zero zero divisors. You can think of this as a field, but without inverses. It's meant to generalize the notion of the ring of integers. In other words, you can think of an integral domain as one way to weaken the definition of a field, but it's not the only weakening that we've seen. In the previous slide, we saw that a division ring is a field, but without the assumption of being commutative. Here, we take the definition of a field and we drop the assumption that non-zero elements have multiplicative inverses, and we get an integral domain. Let's see some examples. First of all, some rings that are not integral domains include Zn when n is composite, because there are zero divisors in here. The even integers, even though that's commutative and has no zero divisors other than 0, that does not have unity. The n by n matrices, that definitely has zero divisors. The product Z cross Z, that has zero divisors. If you take 1, 0 times 0, 1, you get 0, 0. So that's not an integral domain. And then the Hamiltonians, even though it has 1 and no non-zero zero divisors, it's not commutative. Examples of integral domains that are not fields include the ring of integers, the ring of polynomials over the integers or over the real numbers, or the ring of formal power series over the real numbers or over the integers. And here's another one. The ring, we say Z adjoined root M. It's kind of like the definition we had on the previous slide, but now our coefficients are integers instead of rationals. So Z adjoined root M is a set of all A plus B root M, where A and B are integers. This is an integral domain, but it's generally not a field. For example, it contains the integer 2, but it does not contain its multiplicative inverse, 1/2. I should mention that this term domain is also the topic of my chapter 9, and domain means a ring that has no non-zero zero divisors. And integral just means it's a commutative ring and it has 1, so it behaves like the integers. So in chapter 9, we'll see other examples of domains. We'll see principal ideal domains, Euclidean domains, and other things. And most of these, we will assume that the ring is commutative, so they will be integral domains with extra conditions. Now that we've defined the fundamental terms, let's look at some consequences and results. So when doing basic algebra, this is lowercase a algebra, like what you learned in middle school and high school, we often take for granted fundamental properties like cancellation. In other words, if ax equals ay, then of course x equals y. But this need not hold in all rings. For example, in Z6, 2 is just 2 times 1. But it's also 2 times 4, because 2 times 4 is 8, which is 2 mod 6. But 1 and 4 are not the same. So this is an example of where 2 times 1 equals 2 times 4, but 1 is not equal to 4. In the ring of 2 by 2 matrices, it's easy to find examples where you have A times B equals A times C, but B and C are different. And here's one such example of matrices where both times the product is the matrix 1, 0, 0, 0. So what's going on here? Why does cancellation fail, and in what rings does it hold? It turns out that everything works fine as long as there aren't any non-zero zero divisors. Formally, if R is an integral domain and A is a non-zero number, then AX equals AY implies X equals Y. So how do we prove this? There's not much we can do. So let's just suppose that AX equals AY. And now, what do you think? Well, we can subtract these things and write AX minus AY equals 0. And we can factor out an A, right? That is A times X minus Y equals 0. And if we are in an integral domain, that means either A is 0 or X minus Y is 0. But we've assumed that A is not 0. So since A is not 0, X minus Y must be 0. And therefore, X equals Y. And that's what we wanted to prove. In the first 2 videos in this chapter, I've mentioned that finite rings are almost non-existent in most algebra books and classes, except for finite fields. And that might seem strange because in the previous lecture, we saw just how many finite rings there are. For example, it's not even known how many there are of order 32. But most of those are non-commutative and without unity. So in this slide, I'll give you a reason for perhaps why finite rings aren't all that common. So first of all, a remark. If R is an integral domain and we have a non-zero element A, then every power of A has to be non-zero. Do you see why that is? Because if A to the K was equal to 0, then that would imply that A times A to the K minus 1 was equal to 0, but that's not possible in an integral domain. One consequence of this is that every finite integral domain is a field. So maybe that's why we don't see finite rings very much because there aren't any finite integral domains other than the ones that we do see, which are fields. Let's prove this. So let's say that R is a finite integral domain. Sometimes we write IR. And A is a non-zero element in R. To show that R is a field, we just have to show that A has a multiplicative inverse. So consider the sequence A squared, A cubed, A to the fourth, A to the fifth, etc., which, because the ring is finite, this must repeat. So all we have to do now is find two powers of A that are the same. So find some A, or say I, bigger than J, with A to the I equaling A to the J, which is possible because this is a finite ring. And once we have that, then we can say, then A to the I minus A to the J. Well, that's on one end, that's 0. But that's also equal to, well, we said J was smaller, right? So we can write that as A to the J times A to the I minus J minus 1. And so if we're in an integral domain, and we know that every power of A is non-zero, so we know that this is non-zero, well, that means that this term must be 0 because their product is 0. So in other words, A to the I minus J minus 1 equals 0. But what does that mean? That means that A to the I minus J equals 1. And that means that, and remember, I is bigger than J, so A times A to the I minus J minus 1 equals 1. And there is the multiplicative inverse of A. And that's all we had to show.